Hey guys, today we're going to do lesson 6.5, which is called numerical integration, but that's a really strange title. It's really the Simpsons rule and the trapezoid rule. So we're going to work on the trapezoid rule and the Simpsons rule, which is really backwards. So this lesson is really out of place compared to the ones that we've done. So this book likes to do integration and then rolls from integration into definite integration. So we did indefinite integrals and now we're doing definite integrals. And then at the very end of the everything, they talk about how to do it the old school way, which is using Riemann sums and the trapezoid rule and the Simpsons rule. Now, we're not going to do anything with Riemann, really. A lot of Riemann sums are not as accurate, and they take a lot more time than the trapezoid rule and the Simpson rule. Not that the trapezoid rule and the Simpson rule are simple, they take a lot more time than actually finding the integral. But it's very important that we understand where the foundation and the building blocks for all of this come from. Now, like I said, normally you would do Riemann sum, trapezoid rule, Simpson's rule, all the way back in the beginning of chapter 5, really, instead of doing them all the way at the end of chapter 6. But our book always puts them last, which is fine. It works okay that way because we flow from derivatives into integrals, and we just talk about integrals being the opposite of derivatives rather than integrals being a compilation of the area underneath the curve. Okay, so just to take you on a quick walk down memory lane, we talked about Riemann sum a little bit the other day. So Riemann was just a guy, and his formula allowed us to create the area under a curve by taking a bunch of rectangles that were connected on either the left side or the right side. It didn't matter. You could do left-handed rectangles or right-handed rectangles. And you run them up to the curve on whichever side you're doing. I did the left-sided rectangles. Draw the rectangle straight across, drop it down, and then you would find the area of each rectangle, add up those areas, and that would be your estimated area of the area under the curve. And then you would shrink the rectangles down, and then you would shrink the rectangles down, and then you would shrink the rectangles down. And we found that the smaller that we make the rectangles, the more accurate the area becomes. And if you could make the rectangles infinitely small, in other words, just lines, you would get a really good estimate of the area of that entire curve. And what that is the integration process. We shrink the width of the rectangles down until they're so thin that we end up with the exact area of the curve sitting right there. Now, there were a couple of people, one of which was Simpson. I don't know who made the trapezoid rule, but there were a couple of people who came after Riemann that said, there are better estimators. Now, we understand that this just eventually, by Newton and Leibniz, turned into an integral. Boom, done, end of story, right? But along the way, in between, we built two other rules to get more accurate results of what we were actually looking for, which was the area under curves. And they're called the trapezoidal rule and the Simpsons rule. So the first person who came along said, rectangles are all well and good, but I know how to do the area of a trapezoid just as easily as I know how to do the area of a rectangle. So what if I find the area of every trapezoid under the curve and sum them up? And so the basic area is, trapezoid area is 1/2 base 1 plus base 2 divided by, or times height, sorry. 1/2 base 1 times base 2 times the height. Okay. Now, if you keep your height consistent, that multiplier, the height, can come all the way out front. This 1/2 belongs to every trapezoid, so we can take that out front. So if I have my second trapezoid, that would be 1/2 base 2 plus base 3 times the height. Now I want to explain that real quick. So this is the first base of my first trapezoid, base 1. This base 2, is shared by both this first trapezoid and this second trapezoid. So the second trapezoid has base 2 in common with the first trapezoid's base 2. And that's actually going to help us make the formula even easier in the end. And then base 3 is over here. Now base 3 is shared with this trapezoid over here that has base 3 and base 4. And base 4 is shared with this one that has base 4 and base 5. And base 5 is shared with this one that has base 5 and base 6. And base 6 is shared by this one that has base 6 and base 7. But base 1 and base 7 are not shared by any other trapezoid. Therefore, they don't need to be interconnected through the trapezoids. All right, so now, next step was to combo all this together. Like I said before, all the formulas have a half, so I'm going to pull out all the halves. Boom, 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 boom. All the formulas have the same height, assuming that you make the width of the segments the same. So I'm going to pull out all the h's. So now I have 1/2 h, which we're going to say is h over 2 times base 1 plus base 2 plus base 2 plus base 3 plus base 3 plus base 4 plus base 4 plus base 5 plus base 5 plus base 6 plus base 6 plus base 7. Oh, okay, so this is a lot of junk, but this can be simplified because I have 2 base 2s, 2 base 3s, 2 base 4s, 2 base 5s, 2 base 6s. So when we pull this all together, h is going to be my width. I'm actually going to change its name to delta x. So I have delta x over 2 times base 1, which we're going to call fx1. In other words, it's the y value when we plug in this x value, whatever that x value is, plus, I have 2 base 2s, so I'm going to write that way, 2 times fx2, which is the y value at this second x value, plus 2 times fx3, etc., all the way to our last base, which we're going to call fxn. That completes our trapezoidal rule. You want 1 of the first base, you want 1 of the last base, but you want 2 of all the bases in between. You add all this junk together, times it by your height or width or whatever you want to call it, divided by 2, and you have the estimated area of that whole zone. Now, Simpson's rule came along a little further with a guy named Simpson who decided, I can do one better. I can turn all of these into tiny parabolas. And the tiny parabolas will be all vertex, vertex, and or they'll be endpoint, endpoint, vertex, endpoint, endpoint, vertex, endpoint, endpoint, vertex. Now, I don't want to get into too much detail on Simpson's rule because I feel like the detail and how the formula is actually built will be more confusing than it's worth. The trapezoidal rule is very easy to just see and picture in your mind, which is why I wanted to lay it all out, start to finish. But the Simpson's rule is a little trickier. So I don't want to go into the detail on how the whole formula works, but this is the basic system. Simpson's rule is a slightly better estimator than the trapezoid rule, by the way. Riemann leaves lots of space, top and bottom. unless you can shrink the rectangles down really small. The trapezoid rule leaves a tiny bit of space, top and bottom, okay? The Simpson's rule leaves an even tinier amount of space, top and bottom. Now Simpson's rule is delta x, which is the width. These are delta x, whatever your width is here, divided by 3 times fx1. I only have one base on the front. Now, the really tricky thing about Simpson's rule is the second base will actually get used 4 times. So I have 4fx2. And I don't want to go into too much detail on how that is, but it ends up being jumped through several parabolas. The third base only gets used 2 times though, fx3. And then the bases rotate back and forth. 4, 2, 4, 2, 4, 2, 4, 2, until you hit the last one. Whatever your last one is only gets counted once. So the first and last base only get counted 1 time. In the trapezoid rule, they go 2, 2, 2, 2, 2 in the middle. In the Simpson's rule, they go 4, 2, 4, 2, 4, 2 across the middle. Okay? Now, I'm going to do an example of each rule, and then I'll release another video where I'll do a couple of homework problems, and I'll ask you to do the homework, and that's our week this week. So you got this one video of lecture. Make sure you get really, really good notes, and then you're going to have a video of homework, and then you're going to have an assignment to do, and that's this week. Now next week, we're looking at the book review, so I want everybody to work at least a handful of problems, and I'll create a video on it, but I'm going to ask you to work at least a handful of problems in each section on the book review, and then I'm going to send out the test, like I said before, only it's not going to count as a test. I'll put it in probably as like a 20-point quiz, and we'll work it like a worksheet. If you guys want to help each other, work together, it's fine. Whatever's fine, as long as it gets done, and gets done correctly. All right, so I'm going to go into the book and do a couple of examples here. I'll rewrite the rules here in a second so that you can see them nice and clear. I'm going to do one example of each rule, by the way. So the first example is on page 416. It's example 5.2. And this is a trapezoidal rule example. So just to remind us of the trapezoidal rule, it's delta x over 2 times f x1 plus 2 times f x2 plus 2 times f x3, etc., down to f xn. Remember, there's only one of each end point. Now they want us to calculate, in example 5.2, the integral from 1 to 2 of 1 over x with n being 10. Now before we do that, I want to talk about the actual integral. So the actual integral, if you went and calculated it, the integral of 1 over x is ln. So this would be the zone from 1 to 2 of the ln of x, which gives us the ln of 2 minus the ln of 1. And the ln of 2 minus the ln of 1 is approximately 0.69314 7181. It's in that neighborhood. So we're hoping to come somewhere near that zone, because that is the actual area of what we're looking at, okay? But now let's come back to the actual problem and what it's asking us to do. So we need to break up the zone from 1 to 2 into 10 tiny pieces. Now the 10 tiny pieces means we'll actually have 11 values, because you have your start and your end, and there's 10 sections in between. If I break up one unit into 10 sections, I'm breaking them up by 1/10. So my zones are 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Those are the zones that I need to break this up into. Now my delta x is the distance in each zone, which is 0.1. So let's drop into our formula here. So delta x is 0.1 over 2. Now you can do that in a second. Half of 1/10 will be 1/5, and we'll get it here in a second, right? Now, we're going to do f of 1, because that's our first value. So we're going to put 1 in for x in the formula. 1 over 1 is 1 plus 2 times. Now we're going to put 1.1 in the formula. So we're going to do 1 divided by 1.1, and then we're going to times that by 2, and that's 0.909. Now I'm going to put 1.2 in. 1 divided by 1.2. You know, I'm going to maybe keep it as a fraction. Let's go back and do the first one as a fraction. Maybe that'll help. 1.1, so 1 divided by 1.1, and then switch it to a fraction. That would be 10/11. And then 1 divided by 1.2, switch it to a fraction, that'll be 5/6. 1 divided by 1.3, switch it to a fraction, that's 10/13. 1 divided by 1.4, switch it to a fraction, that's 5/7. 1 divided by 1.5, switch it to a fraction, that's 2/3. 1 divided by 1.6, switch it to a fraction, that's 5/8. 1 divided by 1.7, switch that to a fraction, that's 10/17. 1 divided by 1.8, switch that to a fraction, that's 5/9. 1 divided by 1.9, switch it to a fraction, that's 10/19. 1 divided by 2 is 1/2. Now hopefully everybody is seeing where I'm getting my values. Because my function is 1 over x, I should be 1 divided by whatever my x value is at each layer. Okay. Oh, this should be a hard bracket. Alright, now I'm going to add up everything on the inside, and then I'm going to times by 0.1 divided by 2, which is 0.05. 1 plus 2 times 10/11 plus 2 times 5/6 plus 2 times 10/13 plus 2 times 5/7 sevenths plus 2 times 2 thirds plus 2 times 5/8 plus 2 times 10/17 plus 2 times 5/9 plus 2 times 10/19 plus 0.5. So this is approximately 13.87542806. And I'm going to times that by 0.05, and I get 0.693771403. Compare that to what I had up there, 0.69377 versus 0.69314. It's a pretty good estimator. Now we ended up with a little bit of bonus area when we ran the trapezoidal rule here. Hopefully everybody was able to follow that kind of okay. Now I'm going to kick into Simpson's rule, which is the next rule. So it's the exact same formula here though. So we're going to go into the same zone, which is nice here because it's set, I already have it set up. Now you're going to find that on the homework. What they're going to ask you to do is both rules on each problem. So don't reinvent the wheel when you're going from one problem to the next. So all the problems are going to say, do this with the trapezoid rule, do it with the Simpson rule. Okay, so just it's a part A, part B situation. Don't reinvent the wheel. We're going to do the same 10 chunks. We're in example 5.4 now, which is a Simpson rule. Just remember how they're different. So Simpson's rule is delta x over 3 times, and then it's fx1 plus 4 fx2 plus 2 fx3 plus 4 fx4, etc. down to, I should have kept that stuff in the bottom, fxn. That was silly of me. All right, so I really I screwed up with the fact that I should have kept my fractions, but it's fine. I kept my numbers up top. So my delta x is the same, 0.1 divided by 3, which is a slightly different number. 0.1 divided by 3 is not 0.1 divided by 2. That's going to be 1/30th. And then 1 over 1 is 1, plus 1 divided by 1.1 is 10/11ths, but that's 4 times 10/11ths. 1 divided by 1.2 is 5/6, is 2 times 5/6. 1 divided by 1.3 is 10/13ths, 4 times 10/13ths. 1 divided by 1.4 is 5/7, so that'd be 2 times 5/7. 1 divided by 1.5 is 2/3, so that'd be 4 times 2/3. 1 divided by 1.6 is 5/8, so it'll be 2 times 5/8. 1 divided by 1.7 is 10/17, so it'll be 4 times 10/17. 1 divided by 1.8 is 5/9, so it'll be 2 times 5/9. If you had these on the previous rule, you could just copy down the fractions because they're all the same. 4 times 10/19, and then 1/2. Which is what I should have done, but I didn't. So now I can just roll through and figure out what the inside is. So I have 1 plus 4 times 10/11 plus 2 times 5/6 plus 4 times 10/13 plus 2 times 5/7 plus 4 times 2/3 plus, I just lost that. I think I got it. Plus 2 times 5/8 plus 4 times 10/17 plus 2 times 5/9 plus 4 times 10/19 plus 0.5 times 1/30. I must have screwed something up. Let me try again. That's what I was afraid of. 1 plus 4 times 10/11 plus 2 times 5/6 plus 4 times 10/13 plus 2 times 5/7 plus 4 times 2/3 plus 2 times 5/8 plus 4 times 10/17 plus 2 times 5/9 plus 4 times 10/19 plus 0.5. So I have 20.79-ish. And then I multiply that by 1/30 times 1/30, and I get perfect 0.693150.231. Now, as you'll see, that is closer to what we have. Actually, 0.69314, 0.69315 is closer than what we got in our trapezoid rule. However, it's still not a perfect estimator. You would have to shrink down your delta x significantly more to get to the point where it would be a perfect estimator.